You hear about Mars, moon bases, even asteroid mining, but there's one place almost nobody seriously talks about sending people to, because everybody who runs the numbers quietly hits the same wall: Saturn. Not because it isn't beautiful, not because we don't want to go, but because once you cross that line out there, something about the trip changes from mission to point of no return. In this video, we're going to walk straight toward that line, peel back the layers of what it would actually take to reach the ringed giant, and see why every step closer feels less like planning a visit and more like volunteering to disappear from Earth forever. But before we continue, please subscribe to the channel to give your support. Let's continue. You say you want to go to Saturn and come back, but the very first problem is brutal. The distance behaves like a built-in one-way filter, and you only really see it when you look at the numbers. Start with where everything actually is. Earth orbits the Sun at about 100 million kilometers. That's 93 million miles. Saturn orbits at around 1.4 billion kilometers, roughly 870 million miles. That means depending on where both planets are in their paths, the gap between Earth and Saturn is about 1.2 to 1.7 billion kilometers, roughly 750 to more than a billion miles. At some alignments, that's up to about 11 times the Earth-Sun distance sitting between you and home. This isn't just farther than Mars, this is a different regime entirely. Now ask yourself, if that gap is so large, how long does even light take to cross it? Light moves at about 300,000 kilometers per second, around 186,000 miles per second. Even at that speed, the one-way travel time to Saturn can be around an hour or more, and the round trip, signal out plus signal back, can easily be 2 hours or more when the geometry is bad. So when you send a message from Saturn, nobody on Earth hears it now. They hear it after a long, unavoidable pause. Every conversation with mission control, every emergency question, every personal call to family is delayed by physics itself, not by bad Wi-Fi. If even a beam of light takes hours to go there and back, what does that imply for a slow, massive spacecraft carrying fragile humans? Next level of the trap: travel time with the engines we actually have. Right now, human spaceflight depends on chemical rockets. These are powerful at launch, but they are not magic. To go from Earth's orbit to Saturn's orbit, you can't just point the rocket and burn full thrust for years. You don't have that much fuel. You have to use careful transfer orbits and gravity assists, waiting for the planets to line up so you can fall along an efficient path. With realistic trajectories and current propulsion, you're talking about roughly 6 to 8 years one way to get a crew there in a way that doesn't kill them. That's not a long trip, that's a major chunk of your life. Cassini is the real benchmark here. It launched in 1997, used gravity assists from Venus twice, then Earth, then Jupiter, and only reached Saturn in 2004, nearly 7 years of flight. And this was a lean, unmanned probe. No heavy crew habitat, no thick radiation shielding, no food and water for people. You cannot expect a human ship, which is much heavier and must be much safer, to beat that time by some huge margin. So already, before you think about getting back, you are looking at almost a decade just to arrive. And if 7 or 8 years is the one-way travel time, how stable do you think your health, your technology, and your support on Earth will be over twice that span? Then comes the energy bill, which is where the distance really turns into a wall. Earth moves around the Sun at about 30 kilometers per second, roughly 67,000 miles per hour. Saturn is slower, about 9.7 kilometers per second, about 21,700 miles per hour. To meet Saturn safely, your spacecraft has to change its own orbit around the Sun so that it ends up moving at almost Saturn's speed, in Saturn's lane. That speed change is measured in several kilometers per second of delta V, which just means how much you have to change your velocity over the mission. It doesn't sound like a big number, but in rocketry, every extra kilometer of required speed change pushes your fuel needs up extremely fast. The key idea is simple. Your rocket has to carry the fuel that will be burned later, and that fuel itself has mass. So when you accelerate, you're not only pushing the ship and the people, you're also pushing all the fuel you still plan to burn. For a mission to Saturn, you need energy to leave Earth's gravity, to shape your solar orbit, to adjust during cruise, and then to slow down enough to be captured by Saturn's gravity without just slingshotting straight past it into the outer dark. Each of those steps costs speed, and each speed change costs fuel. By the time you stack all of that onto one mission plan, your energy bill is not just high, it's punishing. Now take that already heavy bill and ask the hard question. What happens when you insist on going there and coming back? Every meter of speed change that you want for the return leg has to be planned for from the very start. That means the fuel for your trip home has to be launched from Earth too, sitting in tanks either on your ship or on some fuel depot you rendezvous with. Because fuel must accelerate fuel, the total mass doesn't just double when you want to double your useful speed change. It can increase by many times. For a full Saturn mission with a safe return, the amount of propellant you would need pushes your launch mass into absurd territory. Think about it in simple terms. You end up launching an enormous stack, most of which is just propellant and tanks and structure to move a small living volume where the crew actually stays. You are using a skyscraper-sized pile of fuel, maybe spread across several giant rockets assembled in orbit, to give a small cabin the ability to go out and come back. At some point, this starts to look less like a practical mission and more like an engineering stunt that no one wants to pay for, especially when there are closer targets like Mars that give you much better science per kilogram of fuel. And we still have one more basic but brutal constraint: timing. You can't say, we'll launch when we're ready. In interplanetary travel, you launch when the orbits line up. Earth and Saturn are both circling the Sun at different speeds, and there are only certain windows where a transfer orbit is efficient in terms of fuel. For Saturn, these windows can be separated by years. Miss one, and you wait. Hit one, and you're locked into a long, fixed timeline. So you leave during one window, you arrive 6 to 8 years later, and then you discover another problem. The next good window to return might not coincide with the time you plan to leave Saturn. That means you might have to wait in Saturn orbit for several extra years just to get a fuel-efficient shot back to Earth. Now your mission is 7 out, 3 to 5 waiting, 7 back. You're pushing 17 to 20 years commitment, and that's if everything goes relatively well. Your body has to survive that. Your ship has to survive that. And the civilization that launched you has to stay stable and willing to fund you for that entire span. When you stare at those times and those distances honestly, the conclusion starts to form. Saturn, with today's technology, is not a place you visit and then casually return from. It's a place that turns you into a long-term resident by default. So if the distance, the light-hour communication lag, the multi-year travel time, the huge energy bill, and the tight orbital windows already push the mission toward one way by design, what happens when you add the raw mathematics of rocket mass and fuel on top of that and see how fast a round trip explodes into something almost nobody will ever build? You've probably heard people say, just add more fuel and go farther. But for a Saturn mission with a return ticket, that idea is almost backwards. The more fuel you add, the more the math pushes you toward never coming home. Here's the core problem: the rocket equation. You don't need the formula, you just need the logic. Your ability to change speed, what engineers call delta V, depends on two main things: how efficient your engine is, and how much of your starting mass is propellant instead of useful stuff like crew cabins and life support. But the relationship is not linear. If you want a little bit more delta V, you add some fuel. If you want a lot more delta V, you don't just double the fuel, you often have to multiply it many times, because every extra kilogram of propellant also has to be pushed by the engine during earlier burns. So for a Saturn mission, list out what you need delta V for. You have to get off Earth, climb out of Earth's gravity, then change your orbit around the Sun to intercept Saturn, then slow down enough to be captured by Saturn's gravity, then do maneuvers inside the Saturn system. That's already a big stack of speed changes. Now, mirror that whole sequence in reverse for the trip home. Every one of those steps adds to the total. By the time you add outbound and inbound together, the delta V budget starts to look less like Apollo to the moon and more like a theoretical exam problem nobody expects to fly in real life. Here's the paradox. Adding a safe, comfortable return leg doesn't just add a little extra fuel to your design, it pushes your total fuel requirement into a range where your rocket is mostly tank and almost no ship. The more serious you get about a round trip, the more the math quietly votes for a one-way mission. So you might push back and say, fine, then don't do it in one shot. Just build a giant rocket, something bigger than anything we have, and brute force it. That's where staging hits you. Look at the Saturn V, the rocket that sent humans to the moon. It was about 110 meters tall, roughly a 36-story building, and it could push around 45 tons of payload onto a path toward the moon. That's about 45,000 kilograms, or close to 100,000 pounds, heading out of Earth orbit. That sounds huge, but in deep space terms, it's not. A human Saturn ship with all its life support, radiation shielding, structure, and especially round-trip fuel would be far heavier than that. You're not sending a small lunar lander and a tiny command module for a week-long mission. You're sending a traveling space station for decades. So one Saturn V doesn't cut it. You'd need multiple Saturn V-class launches just to get all the segments and propellant into Earth orbit. Then you have to bolt them together in space, transfer fuel, check everything, and only then even start the interplanetary part. And that's assuming we still had Saturn V. In reality, you'd probably need an entirely new class of super heavy lifters, bigger than anything flown so far, each one expensive, complex, and risky. You're not talking about a single heroic launch, you're talking about a whole program of massive rockets just to assemble one ship that, after all that effort, is still fighting the same rocket equation once it leaves Earth. At some point, mission planners look at this and say, is it really rational to treat this as a round-trip vacation, or does it make more sense to treat it as the start of a permanent outpost? Then maybe you try a different angle. If hauling all that propellant from Earth is so painful, why not make at least some of it out there, refuel in space, turn Saturn into a gas station? This is the idea of in situ resource utilization, or ISRU. On Mars, this is at least somewhat realistic. There is a solid surface you can land on, there is carbon dioxide in the atmosphere, there is ice in the ground. You can imagine factories that pull in CO2, split it, and make methane and oxygen for rocket fuel. Hard, but not absurd. Now look at Saturn. There is no solid surface you can land on. Saturn is mostly hydrogen and helium, with the gas gradually getting denser and hotter as you go deeper. To scoop hydrogen from Saturn's atmosphere, you have to dive into that gas at very high speed, manage insane heating, and somehow contain and compress the gas you collect. The pressures climb from Earth-like to hundreds, thousands, then millions times Earth's surface pressure as you go down. Any scooping vehicle has to survive that environment, slow down, collect material, and then climb back out of a deep gravity well, burning fuel the whole time. Even if you decide to stay in the higher, less hostile layers and just skim the atmosphere, you still have to deal with heating, drag, and the risk of slipping too low, where you simply can't climb back out again. Then you need massive tanks and processing units in orbit, essentially orbital refineries the size of stadiums or bigger, to liquefy, store, and prepare that hydrogen as usable propellant. This is not a small bonus trick. This is a mega project on its own, just to top up your tanks. For a long time, no one is going to build that just so a small crew can go home. So if refueling at Saturn is almost impossible with near-term tech, maybe the solution is to change the engine itself. Don't carry so much fuel. Make each kilogram of propellant do more work. That's where nuclear and fusion concepts enter the conversation. A nuclear thermal rocket uses a reactor to heat hydrogen propellant to very high temperatures, then throws it out the back at higher exhaust speed than a chemical rocket can manage. In simple terms, it roughly doubles the efficiency compared to the best chemical engines. It gives you more delta V per kilogram of fuel. Fusion or advanced electric propulsion could go even further, using plasma drives, ion engines, or fusion reactions to push exhaust to extremely high speeds. On paper, you get huge delta V with far less propellant. But here's the catch. Most of these systems are either experimental or still on the drawing board. We do not have flight-proven, human-rated nuclear thermal rockets flying right now. We definitely don't have working fusion drives in space. And none of these concepts have been shown to run reliably for decades, with constant maintenance, far from Earth, while keeping a human crew safe from radiation and mechanical failure. Until you actually have those systems, tested, proven, and boringly reliable, they aren't solutions. They are wish lists. And even when they arrive, you still have to carry big reactors or fusion chambers, plus heavy shielding, plus radiators to dump heat. All of that is extra mass, and the rocket equation still applies, just with a nicer engine. Until then, the numbers keep pointing to this conclusion. With the technology we use this century, a Saturn mission is much closer to a one-way burn than to a round trip. And even if you somehow solve the propulsion side, you still can't dodge one final issue: the hardware itself. Staging means you drop empty boosters and tanks along the way, from low Earth orbit to interplanetary space to Saturn capture. Those pieces never come back. They're gone. Your main transfer stage might be used up just getting you into Saturn orbit. The big tanks you used to slow down are left behind as dead metal. By the time you're parked around Saturn, the ship that brought you there is a stripped skeleton of what it was at launch. That means your ride home can't realistically be the same vehicle in reverse. To return, you'd need separate hardware, either sent ahead as an unmanned return stage waiting for you, or launched later. But that doubles the cost and complexity again, and every extra rocket launched from Earth to bring you back is money and risk that could instead be used to send more supplies, more crew, more modules, to turn the Saturn presence into a permanent base. From the point of view of a space agency or a future spacefaring company, you start looking at the trade. Do we pay to bring a handful of people back, or do we pay to strengthen the outpost that can push science and industry forward for decades? So when you follow the rocket equation all the way through, you see the pattern. More fuel makes the rocket absurdly big. Staging throws hardware away. Refueling at Saturn is nearly impossible, advanced engines are not ready, and building a separate return bus becomes economically unattractive. The physics of rockets doesn't just make a Saturn round trip hard, it quietly pushes every rational design toward a one-way mission, where the people who go out there are expected to stay. Here's the next problem nobody can ignore. Saturn doesn't just eat fuel, it eats years of your life. And once you add real human biology on top of the mission timeline, the idea of coming back starts to fall apart. So first, look at the clock you're actually flying on. Saturn goes around the Sun once every 29.5 Earth years. That's one Saturn year. The relative geometry between Earth and Saturn, the lineups that give you efficient launch windows, lives on that kind of timescale. Now put your mission on that grid. With today's propulsion, you're talking about roughly 7 to 8 years to get out there, a few years working in the Saturn system, then another 7 to 8 years to get back, if you're lucky with windows and nothing slips. You're very quickly in the range of a 20-year total commitment. If you launch at 30, you're not doing a mission and then coming home to pick up your old life. You are realistically walking back through your front door, if you can still walk, somewhere around 50. And that's in the optimistic case, where your outbound trip doesn't get delayed, your arrival operations don't demand extra years in Saturn orbit, and you don't miss a return window because of some technical problem. Every slip of a year or two pushes your return deeper into your own career and health curve. You're not an active astronaut coming back. You're closer to a retired veteran who spent their prime decades off-world. Then ask, what happens to your body while all this is going on? We already know what a few months in microgravity does from the International Space Station. Even with heavy daily exercise, astronauts lose bone density and muscle. Studies show that in vulnerable areas like the hips and spine, bone loss can reach around 1 to 2% per month without strong countermeasures. Multiply that by years, not months. In a Saturn mission, you have long stretches of microgravity during the cruises, maybe some artificial gravity if you spin the ship, maybe low gravity on moons like Titan, which is only about 0.14 g, roughly 1/7 of Earth's gravity. So your skeleton is spending a decade in a mix of 0 g and very low g. Your muscles are underworked, your heart doesn't have to pump as hard against gravity. Your blood and body fluids shift toward your head. Your eyes can be affected. Your balance system rewires itself for a different environment. Even if you slow this down with exercise and clever medical tricks, you're still asking the human body to tolerate conditions it never evolved for 10 to 20 years straight. By the time you try to come back and stand in full 1G again, it might not just be uncomfortable, it might be physically impossible without severe disability, fractures, chronic pain, maybe a wheelchair for life. So the question becomes, is it ethical to plan a mission where the return means sending people back to a gravity field their bones and muscles can no longer handle? As if that's not enough, your body isn't only dealing with gravity changes, it's soaking up radiation the entire time. NASA and other agencies set rough lifetime limits for astronaut radiation exposure, around 1 sievert, that's 1,000 millisieverts, because beyond that, your cancer risk and other health issues climb sharply. Now look at what a Saturn mission demands. You cross Earth's Van Allen belts on the way out and back. You spend years in deep space, exposed to galactic cosmic rays, high-energy particles that your ship can only partially block. Then you ride out solar particle events, bursts from the sun. Then, near Saturn, you're inside or near its magnetosphere, which traps charged particles and creates its own radiation environment. You can put shielding around the crew, water, polyethylene, maybe even rock or metal, but shielding is heavy. Every extra ton of protection is a ton you're not using for fuel or life support. Over 10 to 20 years, even with decent shielding, the cumulative dose is going to climb. You're not just flirting with the career limit, you're threatening to blow clean past it. That doesn't just mean higher chance of cancer someday. Radiation also hits your nervous system, your cardiovascular system, your immune system. So from a medical point of view, the honest description of a full Saturn round trip is you are deliberately giving a small group of people radiation exposure that most agencies would never approve if they were planning to bring those people back to live normal lives on Earth. As if that's not enough, you might think maybe relativity helps. Maybe time dilation gives you a break. You go fast, you age slower, you come back, and less time has passed for you. That sounds cool, but at the speeds we're talking about, it doesn't happen. Interplanetary cruise speeds are on the order of 20 to 30 kilometers per second. That's about 45,000 to 67,000 miles per hour. Compared to the speed of light, 300,000 kilometers per second, that's tiny, a few 10,000ths of light speed. At those fractions, your Lorentz factor, the thing that tells you how slower your time runs, is so close to 1 that even after years of travel, the difference between your clock and Earth's clock is at most seconds, maybe milliseconds, nothing more. So there is no sci-fi escape here. You don't get to do 20 years of mission time and come back to find that only 5 years passed on Earth, or that you've magically aged less. You age almost exactly in sync with everyone else, just under more stress, more radiation, and more isolation. When you step off that ship, you are not a time traveler. You are someone who spent the prime of their life in a controlled can, committed to a mission that may have already outlived its original ground support team. And that brings up another quiet problem, the time axis of technology back on Earth. Right now, we watch software stacks go obsolete about 5 to 10 years. Operating systems change, programming languages shift, hardware standards move on. A 20-year Saturn mission means the code that runs your ship, your navigation, your life support, and your communications has to be maintained and understood across 2 full generations of tech on Earth. The engineers who wrote it at launch may be retired or dead by the time you're ready to come back. The ground systems they built might be replaced, the original control centers repurposed, the companies that built your hardware maybe don't even exist anymore. On top of that, budgets stop and start. Public interest moves to new crises, new wars, new climate emergencies. The mission that was a flagship project when you left might be seen as an old, expensive obligation when you're asking for $1 trillion return vehicle 15 years later. Support teams get reassigned, supply chains are gone. The people who still care deeply about your return phase might be a small, underfunded group fighting other priorities. So even if your body somehow holds together and your ship is still working, the world that promised to retrieve you might not be willing or even able to pay for the kind of massive effort needed to bring you home. Put all of this together. The mission spans most of your working life, your bones and muscles are pushed near their limits, your radiation dose climbs toward or beyond what we accept today, relativity does not save you, and the world that promised to retrieve you is changing underneath you. The longer you stay tied to Saturn's schedule instead of Earth's, the more realistic it becomes that returning is not part of the plan, not medically, not personally. And after time has already done that much damage to your chances of ever walking on Earth again, what happens when you look at Saturn itself and you realize its gravity well is another deep trap, one more layer of physics that really doesn't want to let your ship climb back out? You hear that Saturn's gravity at the cloud tops is almost the same as Earth's, so it sounds manageable, right? That's the trap. The planet looks friendly on paper, but the energy you need to escape from it is on a completely different level. Saturn's diameter is about 116,000 kilometers, more than 9 times Earth's roughly 12,700 kilometers. It's a huge ball of mostly hydrogen and helium. At the visible cloud tops, the gravity is about 1.07 g, just a bit stronger than Earth's 1 g. So if you could stand there, which you can't, you'd feel only slightly heavier than you do at home. That sounds harmless, but the escape velocity is what really matters for your ship, and there Saturn hits you hard. To get away from Saturn's gravity, starting near the cloud tops, you'd need around 35.5 kilometers per second, about 79,000 miles per hour. Earth's escape speed at the surface is about 11.2 kilometers per second, around 25,000 miles per hour. Saturn's is nearly 3 times higher. That means the gravity well is far deeper in an energy sense, even though your body would feel roughly the same weight. For a spacecraft, that difference is brutal. The extra speed you need to climb away from Saturn translates directly into enormous amounts of propellant. And remember, you're not on the surface, you're in orbit, which adds more complexity. So the paradox is, your body wouldn't feel much different on day one, but your ship is sitting in a much deeper hole, and the bill for climbing back out is way beyond what feels intuitive. So if things are that bad near the planet, why not just stay in a nice, safe orbit and avoid the deep part of the gravity well? Because to do anything really interesting at Saturn, you're pushed downward, toward low orbits, and low orbits are a kind of trap. To study Saturn up close, map its atmosphere, measure its magnetic field, get high-resolution images of the rings, you'd want to operate in relatively tight orbits, not some distant, lazy loop. Cassini's famous grand finale orbits took it skimming between the inner edge of the rings and the upper atmosphere, just a few thousand kilometers above the cloud tops. The closer you are, the faster you move, tens of kilometers per second, and the deeper you are in the gravity well. That means any attempt to raise your orbit, change your inclination, or escape entirely needs more delta V. Every small change costs real speed, and every meter of speed you add or remove comes from fuel. And here's the key link back to Earth. Every kilogram of that fuel was launched from Earth in the first place, at huge cost in money and in launch mass. So being down low around Saturn is not just scientifically interesting, it's also financially and energetically punishing. Once your habitat and main ship are settled into a comfortable low orbit where you can work, the cheapest thing to do, from a physics point of view, is to keep them there. Climbing back out to a trajectory that leads home suddenly looks like the weird expensive option, not the default. So if burning your way out is so expensive, you might ask, why not use the atmosphere to help? The way we talk about doing at Mars with aero braking and aero capture. Trade speed for heat instead of for fuel. The problem is that Saturn's atmosphere is not a gentle brake pedal. It's more like a cliff. At Mars, you can dip into a thin atmosphere at a few kilometers per second, heat up a heat shield and bleed off speed over multiple passes. The air is thin but predictable. At Saturn, you're moving much faster, tens of kilometers per second relative to the gas. The upper atmosphere is very thin, but as you go down, pressure and density ramp up fast and temperatures climb. If you dip a little too deep, drag spikes, you heat violently, and gravity pulls you further in before your engines can save you. You go from slowing down to falling very quickly. If you stay too high, the gas is too thin to matter. You barely shave off any speed, and you've just risked a lot for almost no benefit. The margin between enough drag to capture safely and too much drag, and now you're doomed, is razor thin, and the error bars are not friendly. For a robotic probe, you can sometimes accept that risk. But for a human mission that has to work for decades in a system full of rings, moons, and radiation, you're not going to bet your crew's lives on threading that needle repeatedly. So you end up relying on engine burns to capture into orbit and to adjust that orbit, which puts you right back into the fuel and delta V nightmare you were trying to dodge. So suppose you play it safe. You don't dive deep, you get yourself into a stable orbit where the crew can live and work. How hard is it really to just leave Saturn's system and head home once you're done? First, you have to climb out of Saturn's gravity well, which means boosting your orbital speed relative to Saturn until your trajectory is no longer bound to the planet. That alone can cost several kilometers of delta V, depending on your starting orbit. Then, once you're free of Saturn, you're not done. You're now in a new orbit around the Sun, roughly where Saturn is, moving at about 9.7 kilometers per second, around 21,700 miles per hour. And you need to change that solar orbit to intersect Earth's orbit at the right time and angle. That's another big chunk of delta V. Finally, as you approach Earth, you have to slow down again or use Earth's atmosphere carefully to avoid burning up, which either costs fuel, heat shield mass, or both. When you add all this up, the combined delta V needed to go from a safe Saturn orbit back to Earth can be comparable to or even larger than the cost you already paid to get there in the first place. But now, unlike the outbound leg, your main ship is old. Its tanks are partly empty, its engines have years of wear and tear, its systems have been hammered by radiation and micrometeoroids. Once you've invested enough propellant to capture into Saturn orbit with a full human habitat, the rational thing to do with that hardware, from a mission design point of view, is to leave it there as a long-term station. Treat it as the core of a permanent base. Using it as a throwaway taxi that goes back to Earth is like building a space station and then burning it up in the atmosphere after a few years just because. If this all sounds very theoretical, just look at what we actually did with real missions to the outer solar system. When agencies had to pick between fly by and keep going, or slow down and orbit, they almost always chose the option that avoided deep gravity traps. Voyager 1 and 2 flew past Jupiter and Saturn and never even tried to stop. They used the planet's gravity to change course and speed, then headed outward. New Horizons did the same with Pluto. No braking, no capture, just a fast pass and gone. Cassini is the big exception, and that proves the rule. It needed years of carefully planned gravity assists from Venus, Earth, and Jupiter to arrive at Saturn with just the right speed to be captured. Once it was there, nobody ever pretended it would come back. There was no return phase in the plan. At the end of its mission, it was flown deliberately into Saturn's atmosphere and destroyed, because climbing out and heading home was never on the table. It was cheaper and safer to end it there than to even think about reversing the trip. Now apply that logic to a human mission. You're not allowed the same risk levels. You need slower, safer trajectories, extra propellant reserves, backup systems, thicker shielding, and abort options. All of that adds mass, which demands more fuel, which deepens the gravity trap in very practical terms. So the gravitational logic that already made robots one-way guests becomes even harsher for people. Once you commit to going down into Saturn's gravity well far enough to build real habitats, real labs, real infrastructure, the physics isn't just making your life difficult, it's quietly erasing the idea of a return ticket. And gravity isn't the only invisible field trying to hold you there. As soon as you get close to Saturn, you also move into a vast radiation environment that punishes both your ship and your body every day. And that radiation hits you twice if you insist on leaving and coming back. You're not just sitting in a deep gravity well at Saturn, you're sitting inside a giant invisible radiation machine, and if you plan to cross it twice, out and back, the numbers start to look less like a mission plan and more like a slow medical experiment on your own body. And after time has already done that much damage to your chances of ever walking on Earth again, what happens when you look at Saturn itself and you realize its gravity well is another deep trap, one more layer of physics that really doesn't want to let your ship climb back out? You hear that Saturn's gravity at the cloud tops is almost the same as Earth's, so it sounds manageable, right? That's the trap. The planet looks friendly on paper, but the energy you need to escape from it is on a completely different level. Saturn's diameter is about 116,000 kilometers, more than 9 times Earth's roughly 12,700 kilometers. It's a huge ball of mostly hydrogen and helium. At the visible cloud tops, the gravity is about 1.07 g, just a bit stronger than Earth's 1 g. So if you could stand there, which you can't, you'd feel only slightly heavier than you do at home. That sounds harmless, but the escape velocity is what really matters for your ship, and there Saturn hits you hard. To get away from Saturn's gravity, starting near the cloud tops, you need around 35.5 kilometers per second, about 79,000 miles per hour. Earth's escape speed at the surface is about 11.2 kilometers per second, around 25,000 miles per hour. Saturn's is nearly 3 times higher. That means the gravity well is far deeper in an energy sense, even though your body would feel roughly the same weight. For a spacecraft, that difference is brutal. The extra speed you need to climb away from Saturn translates directly into enormous amounts of propellant. And remember, you're not on the surface, you're in orbit, which adds more complexity. So the paradox is, your body wouldn't feel much different on day 1, but your ship is sitting in a much deeper hole, and the bill for climbing back out is way beyond what feels intuitive. So if things are that bad near the planet, why not just stay in a nice, safe orbit and avoid the deep part of the gravity well? Because to do anything really interesting at Saturn, you're pushed downward toward low orbits, and low orbits are a kind of trap. To study Saturn up close, map its atmosphere, measure its magnetic field, get high-resolution images of the rings, you'd want to operate in relatively tight orbits, not some distant lazy loop. Cassini's famous grand finale orbits took it skimming between the inner edge of the rings and the upper atmosphere, just a few thousand kilometers above the cloud tops. The closer you are, the faster you move, tens of kilometers per second, and the deeper you are in the gravity well. That means any attempt to raise your orbit, change your inclination, or escape entirely needs more delta V. Every small change costs real speed, and every meter of speed you add or remove comes from fuel. And here's the key link back to Earth. Every kilogram of that fuel was launched from Earth in the first place, at huge cost in money and in launch mass. So being down low around Saturn is not just scientifically interesting, it's also financially and energetically punishing. Once your habitat and main ship are settled into a comfortable low orbit where you can work, the cheapest thing to do, from a physics point of view, is to keep them there. Climbing back out to a trajectory that leads home suddenly looks like the weird, expensive option, not the default. So if burning your way out is so expensive, you might ask, why not just use the atmosphere to help, the way we talk about doing at Mars with aerobraking and aero capture? Trade speed for heat instead of for fuel. The problem is that Saturn's atmosphere is not a gentle brake pedal, it's more like a cliff. At Mars, you can dip into a thin atmosphere at a few kilometers per second, heat up a heat shield, and bleed off speed over multiple passes. The air is thin but predictable. At Saturn, you're moving much faster, tens of kilometers per second relative to the gas. The upper atmosphere is very thin, but as you go down, pressure and density ramp up fast, and temperatures climb. If you dip a little too deep, drag spikes, you heat violently, and gravity pulls you further in before your engines can save you. You go from slowing down to falling very quickly. If you stay too high, the gas is too thin to matter. You barely shave off any speed, and you've just risked a lot for almost no benefit. The margin between enough drag to capture safely and too much drag, now you're doomed, is razor thin, and the error bars are not friendly. For a robotic probe, you can sometimes accept that risk. For a human mission that has to work for decades in a system full of rings, moons, and radiation, you're not going to bet your crew's lives on threading that needle repeatedly. So you end up relying on engine burns to capture into orbit and to adjust that orbit, which puts you right back into the fuel and delta V nightmare you were trying to dodge. So suppose you play it safe. You don't dive deep, you get yourself into a stable orbit where the crew can live and work. How hard is it really to just leave the Saturn system and head home once you're done? First, you have to climb out of Saturn's gravity well, which means boosting your orbital speed relative to Saturn until your trajectory is no longer bound to the planet. That alone can cost several kilometers per second of delta V, depending on your starting orbit. Then, once you're free of Saturn, you're not done. You're now in a new orbit around the Sun, roughly where Saturn is, moving at about 9.7 kilometers per second, around 21,700 miles per hour. And you need to change that solar orbit so it intersects Earth's orbit at the right time and angle. That's another big chunk of delta V. Finally, as you approach Earth, you have to slow down again or use Earth's atmosphere carefully to avoid burning up, which either costs fuel, heat shield mass, or both. When you add all this up, the combined delta V needed to go from a safe Saturn orbit back to Earth can be comparable to or even larger than the cost you already paid to get there in the first place. But now, unlike the outbound leg, your main ship is old, its tanks are partly empty, its engines have years of wear, its systems have been hammered by radiation and micrometeoroids. Once you've invested enough propellant to capture into Saturn orbit with a full human habitat, the rational thing to do with that hardware from a mission design perspective is to leave it there as a long-term station. Treat it as the core of a permanent base. Using it as a throwaway taxi that goes back to Earth is like building a space station and then burning it up in the atmosphere after a few years just because. If this all sounds very theoretical, just look at what we actually did with real missions to the outer solar system. When agencies had to pick between fly by and keep going or slow down in orbit, they almost always chose the option that avoided deep gravity traps. Voyager 1 and Voyager 2 flew past Jupiter and Saturn and never even tried to stop. They used the planet's gravity to change course and speed, then headed outward. New Horizons did the same with Pluto. No braking, no capture, just a fast pass and gone. Cassini is the big exception, and that proves the rule. It needed years of carefully planned gravity assists from Venus, Earth, and Jupiter to arrive at Saturn with just the right speed to be captured. Once it was there, nobody ever pretended it would come back. There was no return phase in the plan. At the end of its mission, it was flown deliberately into Saturn's atmosphere and destroyed, because climbing out and heading home was never on the table. It was cheaper and safer to end it there than to even think about reversing the trip. Now apply that logic to a human mission. You're not allowed the same risk levels. You need slower, safer trajectories, extra propellant reserves, backup systems, thicker shielding, and abort options. All of that adds mass, which demands more fuel, which deepens the gravity trap in very practical terms. So the gravitational logic that already made robots one-way guests becomes even harsher for people. Once you commit to going down into Saturn's gravity well far enough to build real habitats, real labs, real infrastructure, the physics isn't just making your life difficult, it's quietly erasing the idea of a return ticket. And gravity isn't the only invisible field trying to hold you there. As soon as you get close to Saturn, you also move into a vast radiation environment that punishes both your ship and your body every day. And that radiation hits you twice if you insist on leaving and coming back. You're not just sitting in a deep gravity well at Saturn. You're sitting inside a giant, invisible radiation machine. And if you plan to cross it twice, out and back, the numbers start to look less like a mission plan and more like a slow medical experiment on your own body. Start with the basic layout. Saturn has a strong magnetic field, not as extreme as Jupiter's, but still powerful enough to carve out a magnetosphere that stretches millions of kilometers into space. That field traps charged particles, protons and electrons, whipping around at high speeds. The result is a huge set of radiation belts wrapped around the planet, a kind of three-dimensional zone where space is filled with high-energy particles instead of just empty vacuum. When you park a habitat in Saturn orbit, you're not floating in some quiet bubble. You're sitting inside that environment. Those particles are constantly hitting your ship and your body. To yourselves, each hit is a tiny bullet, breaking DNA, damaging tissues, and slowly raising your lifetime risk of cancer and other diseases. You can't see it, you can't hear it, but the dosimeters mounted on the walls keep ticking, hour after hour, year after year, and you're planning to live there for a decade or more? We know this isn't just theory because the Cassini spacecraft carried instruments to measure radiation. During some orbits, especially when it cut through certain parts of Saturn's magnetosphere, the radiation level spiked high enough to be a concern even for hardened electronics. That's metal, silicone, and shielding getting stressed. Now translate that to human bodies. Without serious protection, think meters of water, thick layers of plastic, or compacted regolith if you have a moon base, you're looking at doses that can reach into the hundreds of millisieverts over realistic mission timescales. For context, a chest CT scan is about 7 millisieverts. Typical agency guidelines try to keep an astronaut's total career exposure below roughly 1 sievert. That's 1,000 millisieverts, because the data say that beyond that, long-term health risks climb sharply. A Saturn expedition with multi-year cruise phases, years in orbit, and repeated passes through radiation belts is absolutely capable of pushing you toward or past that limit, especially if you're unlucky with solar storms. So you face a simple question. Do you design for safe enough to come back and live a normal life, or do you quietly accept that these people are not coming home to a normal life at all? You might think the answer is obvious. Just add more shielding, make the walls thicker, pack water around the crew quarters, wrap the habitat in protective material until the radiation levels drop. That works up to a point, but then you slam into rocket reality. Engineers often talk about a rough target of maybe 5 to 10 grams of shielding material per square centimeter of surface area as a serious attempt to blunt galactic cosmic rays. Don't get stuck on the units, just focus on the effect. For a modest habitat, say with an external surface area of 100 square meters, which is actually small for a long-term Saturn station, that shielding mass quickly adds up to tens of tons. You're basically hauling the mass of a fully loaded truck, or several trucks, just in extra protective material, on top of everything else. And everything else is already heavy. Structure, air, water, food, recycling systems, reactors or power sources, engines, fuel, tools, spare parts. Every extra centimeter of shielding you add makes your ship bigger, which requires more propellant to push, which requires larger tanks, which adds more mass again. The rocket equation does not care that you're trying to be safe, it just sees more kilograms to accelerate. And radiation doesn't just attack you, it attacks your ship itself. High-energy particles slam into electronics, flipping bits in memory, causing what are called single-event upsets. Over time, sensors degrade, detectors get noisy, materials darken, and solar panels lose efficiency. On a short mission, like Apollo, you can treat radiation damage as background noise. On a 15 or 20-year Saturn campaign, it becomes a central design problem. To cope, you start doing things like triple modular redundancy, where you have 3 copies of a critical system voting on every output, so one flipped bit doesn't crash the spacecraft. You add error-correcting memory, radiation-hardened chips, backup computers, extra cables. You assume that a certain percentage of your hardware will slowly die and need to be bypassed or replaced. That's acceptable if you're building a one-way arc, a station that just has to keep going where it already is. It's much more dangerous if you also need that same hardware to stay healthy enough to handle 2 multi-year interplanetary cruises, a Saturn orbit phase, and then another high-risk re-entry back at Earth. So now you're cornered by a trade you can't escape. Every kilogram of shielding you add to protect the crew is a kilogram you can't use for return propellant. Every kilogram of return propellant you insist on carrying is a kilogram you can't allocate to shielding or to redundancy or to spare parts. The ship design turns into a balance between how much radiation can the humans take and how much fuel can we realistically launch from Earth. If you bias the design toward a safe return, you lighten the shielding, accept higher radiation doses, and trust that everyone will just be okay enough when they get back. That's already a big ethical and medical gamble, and it ignores the hit you take on electronics reliability. If you bias the design to really protect the crew and the systems for decades, you bulk up the shielding, you bulk up the redundancy, your mass explodes, and the idea of also hauling enough propellant for a full round trip starts to look ridiculous. When mission planners run that optimization seriously, the solution that keeps popping out is not go there, stay a few years, then bring everybody back through the same radiation minefield. The solution is go there with enough shielding and infrastructure to survive long term, except that the vehicle is now effectively a permanent station, and accept that the people who arrive will live their lives in that system. In other words, the rational engineering answer to Saturn's radiation environment is not a commuter route, it's a one-way move. And all of this is just from fields and particles you can't see. Once you add real, solid objects into the picture, ice, rock, dust circling Saturn at high speed in the ring system, you discover that even the pretty part of Saturn's neighborhood is hazardous enough to turn your ship into sandpaper long before you've earned the right to talk about coming home. You look at Saturn's rings and they look calm and flat and almost friendly, but the first thing you need to understand is that there is nothing solid and safe about them. They're not a giant highway in the sky. They're a huge, fast-moving debris field that treats your ship like a target. When people see photos, they think disk, like a smooth sheet you could maybe land on or build on. But the rings are actually made of countless separate chunks, from tiny dust grains just a few micrometers across, up through pebbles, rocks, and boulders tens of meters wide. The main bright rings stretch out for about 70,000 kilometers in radial width, roughly 43,000 miles. But their thickness is only on the order of 10 to maybe 100 meters, so from the side, they're thinner than a city block is tall. In practice, that means if you try to move through them, you're not crossing a surface. You're flying through layer after layer of rubble that just happens to be extremely flat when you zoom out. It looks clean from far away. Up close, it's a construction site with no rules. Now think about what those particles are actually doing. They orbit Saturn at huge speeds, around 10 to 20 kilometers per second. That's about 22,000 to 45,000 miles per hour. At those speeds, kinetic energy goes up so fast that even something as small as a grain of sand carries serious punch. A particle that would feel like dust in your hand on Earth hits your hull with the energy of a rifle shot, because speed matters more than size here. You don't need big, dramatic chunks crashing into you to have a problem. It's the invisible micrometeoroids, the stuff you cannot see coming, that slowly sandblast your ship. Over days or weeks, maybe you get lucky, a few dings, minor craters in the outer layers. Over years, if you keep operating near the dense parts of the rings, those hits start to add up. Each one chips away at shielding. Each one raises the chance that a vulnerable line or a sensor or a small tank gets punctured. You're not dealing with maybe once-in-a-career impacts. You're dealing with an environment where micrometeoroid hits are statistically guaranteed over the lifetime of the mission. For a long-term Saturn outpost, the rings are not a pretty backdrop. They're a constant source of mechanical stress that never turns off. So say you still want to get close, you want the science payoff, you want the detailed views, you want access to ring material. Now navigation becomes a nightmare. To keep a station or a big ship near the rings, you can't just park and relax. You have to thread your orbit through BAPs, avoid dense regions, and constantly watch your trajectory relative to trillions of moving targets. Cassini gave us a preview of what up close really means. In its final phase, it dove through the narrow gap between the inner ring edge and the top of Saturn's atmosphere, around 2,000 to 3,000 kilometers above the cloud tops, and the operations team treated every one of those passes like a potential spacecraft killer. They turned instruments away, used a high-gain antenna as a shield on some orbits, and carefully picked paths that minimize risk. Now, scale that up to a human habitat. You don't get to shrug off a bad hit as a loss of hardware. You have people on board. That means more armor, more fuel for constant small course corrections, more sensors, more redundancy. Every time you tweak your orbit to dodge a denser clump, you burn a little propellant. And you already know how painful propellant is when you had to launch it from Earth and maybe drag it all the way to Saturn over 7 or 8 years. The closer you choose to live to the rings, the more your life becomes a continuous avoidance game, like trying to hover a helicopter in inside a swarm of bullets, and the cost of losing focus even once is total mission failure. A lot of people talk about mining the rings, as if they're a convenient open-air store for ice and raw material, just waiting for a clever engineer. On paper, it sounds perfect. You need water for life support and radiation shielding. You need mass for propellant. The rings are almost pure water ice, so just go take what you need. In reality, every harvest attempt is a brutal orbital docking problem at insane speeds. Your ship has to match velocity with ring particles that are already moving 10 to 20 kilometers per second around the planet, then gently capture some of that material without smashing itself apart. Think about that. Your ship is basically trying to fly next to a cloud of shrapnel, moving faster than a rifle bullet. Reach out, grab some, and back away without taking a hit that blows a hole through a tank or a critical module. You can design armored scoops. You can try to dip it in and out quickly. You can use robots, but the statistics are against you. The more passes you make into dense ring regions, the higher the chances that sooner or later, a piece of debris hits something vital. You might pull out enough ice to thicken your walls or feed your life support, or you might get shredded before you fill your first storage tank. As a long-term supply strategy, we'll just mine the rings is not a proper plan. It's a gamble with your entire habitat as the stake. So if being close to the rings is that hostile, what's the sensible move? The straightforward answer is to stay well outside the densest parts, in orbits that line up with some of Saturn's moons like Titan or Rhea, or even farther out. That way, the worst of the ring debris is always inward from you, and you only deal with the lower density dust and rock present in the wider system. But that choice has a cost too. If you stay far, you don't get easy access to ring ice, which kills most of the locally sourced shielding and propellant fantasies. You rely mostly on what you brought from Earth, maybe topped up with resources from larger moons if those turn out to be usable. In that scenario, your station design shifts. You stop thinking like a ship that will move around Saturn a lot, and you start thinking like a fortress in orbit. Thick armor, minimal exposed area, fixed orbit, almost no unnecessary maneuvers. You build something that can sit in one place relative to the planet and just survive year after year without constant close passes through risky regions. But a structure like that, once built, is not a good candidate for going anywhere. It's bulky, heavy, not streamlined for thrust. It's more like a town built in space. Towns don't lift off and fly across the solar system, they stay put. So in the ring system, you face the same pattern again. The option that keeps people alive is to build something stationary, heavily protected, and cautious. And that architecture is the enemy of any plan that says, and then one day we all pack up and fly back to Earth. The safer you make life near Saturn's rings, the more you lock the crew into being permanent residents. And the rings are only the debris problem, because just beneath them there's an even worse environment waiting, an atmosphere with no solid ground, where there is literally nowhere to land. And once you go down there with people on board, you are not climbing back out. You're used to a planet meaning there's ground somewhere, a place you can land, park a ship, drill, refuel, and take off again. But Saturn quietly breaks that idea. There is no floor. And once you really understand what that means, you see why any serious descent with people is basically a one-way drop. Saturn is mostly hydrogen and helium. That's it. Gas and more gas, with maybe a dense core deep inside that you are never going to reach alive. There is no solid surface in the normal sense, no clear line where space ends and a ground begins. As you descend from orbit, you pass through upper haze layers where the pressure is around 1 bar, like Earth's sea level. Then you keep going, and the pressure just keeps climbing. Tens of bars, hundreds of bars, then thousands, then millions of bars deeper down. At the same time, temperature starts around minus 130 degrees, roughly minus 200 degrees Fahrenheit, in the upper atmosphere, and then climbs to hundreds of degrees, then thousands of degrees as you get crushed deeper into the planet. There is no safe plateau, no stable platform, just gas getting denser and hotter with depth, until everything you know how to build just fails. So the obvious question is, what actually happens if something falls in at real entry speeds, not in a slow, gentle elevator ride? A probe coming in from orbit is moving at tens of kilometers per second, easily 20 kilometers per second and up. That's around 45,000 miles per hour and up. When it hits the upper atmosphere, it doesn't meet air. It meets a wall of gas that it slams into so hard that the gas in front of it gets squeezed and heated to plasma temperatures. That's what gives you the bright fireball of re-entry. You can use a heat shield. You can try to slow down, but that only buys you some time. Once you get below the thin top layers and start dropping a few hundred kilometers down, the pressure ramps up fast. At a few tens of bars, most human hardware is outside its comfort zone. At hundreds of bars, you are in a regime where unreinforced steel, normal windows, standard seals, all of that is just crushed or deformed. Remember Galileo's Jupiter probe? It entered Jupiter's atmosphere, transmitted data for about 58 minutes, then the increasing heat and pressure simply destroyed it. And Jupiter and Saturn's atmospheres are in the same rough category, deep gas giants with brutal interiors. Nobody's sending a human crew into that and expecting them to climb back out. And below the levels where even a hardened probe can survive for an hour, the physics turns truly hostile. Go deep enough and the hydrogen that started out as a normal gas gets squeezed into a strange state called metallic hydrogen. You're talking about pressures on the order of 1 to 4 million bars and temperatures of several thousand Kelvin, thousands of degrees Celsius, hotter than the surface of many red dwarf stars. In that state, hydrogen behaves more like a metal. It conducts electricity. It helps drive Saturn's magnetic field and internal heat flow. That's fascinating for physics, but for equipment, it's instant death territory. You are not putting mining rigs down there. You are not building platforms. You are not drilling in that environment. The materials fail. The electronics fail. Even the structure of your vehicle would be crushed and cooked almost immediately. So maybe you try to dodge the whole deep interior problem and ask a different question. Could we just float? Could we stay in a sweet spot at the right pressure and temperature and never touch the deadly layers below? In theory, yes, you could design aerostats, floating platforms, or balloon cities that hover in Saturn's atmosphere. At around 1 bar pressure, you have something like Earth's sea level pressure, and the temperature up there is around minus 130 degrees Celsius, about minus 200 degrees Fahrenheit. That's super cold, but we know how to insulate against cold. If you fill a balloon with hot hydrogen, which is lighter than the colder hydrogen around it, you can get buoyancy. You can float. On paper, you can pick a layer with Earth-like pressure and build a cloud city. But the practical problems are ugly. Winds in Saturn's atmosphere can reach hundreds of meters per second. That's up to around 1,800 kilometers per hour, roughly 1,100 miles per hour. That's faster than Earth's strongest hurricanes, and it's not a temporary storm. It's part of the global circulation. Your floating city has to survive constant high-speed winds, shear layers where different altitudes move at different speeds, vertical motions, and turbulence. You need active control to keep your platform oriented, to keep it from rolling, pitching, or being dragged into zones where it starts to sink. And nothing is anchoring you. On Earth, a floating platform can tether to the seafloor. A tower can bolt into rock. On Saturn, there is no anchor. You are just hanging in a fluid, supported by buoyancy. If a balloon envelope tears, if you lose internal pressure, if a structural element fails, you don't land and roll to a stop. You lose lift and begin to sink deeper into denser, hotter gas. And the deeper you go, the harder it is to get back to that safe layer, because the buoyancy conditions change and the environment gets more violent. At some depth, your structure and your people are simply destroyed. So a floating habitat is not the same as a safe platform. It's a complex machine that must work 24/7 for decades, because one serious failure and you're on a path that only goes down. Now zoom back out to mission design and ask the simple, brutal question. What about a crewed vehicle that dips into Saturn's atmosphere on purpose? Maybe for science, maybe to sample gas, maybe to demonstrate capability. Is that ever part of a round trip? Realistically, no. Any manned vehicle that dives meaningfully into Saturn's atmosphere is on a one-way trajectory by definition. To enter, you have to give up orbital speed. You have to fall into the gravity well and let drag slow you. To get back out to orbit, you need to reverse that process. You need enormous delta V to climb while fighting both gravity and drag. That means a huge engine, massive propellant reserves, and a structure that can survive both the entry and the climb. all wrapped in enough shielding to keep the crew alive. By the time you design such a craft, it stops looking like a science sub and starts looking like a full interplanetary ship. And you still haven't solved the problem of refueling it, because there is no surface with tanks and fuel plants waiting. If it enters from orbit and goes deep, it's not coming back. The only sane way to do atmospheric exploration at Saturn in the near term is with uncrewed probes that you accept as disposable. They go in, send data for as long as they can, then they die. If you ever include atmospheric operations with humans, those operations are essentially a branch of the mission that does not return, by design. You either keep the crew in the upper layers on floating stations forever, or you send them in once knowing that there is no realistic way to pull them back up to orbit and then all the way back to Earth. So now you have a planet with no floor, an atmosphere that turns entry into a furnace and descent into a crush zone, and floating solutions that are only safe as long as nothing important ever fails. In that environment, the concept of we'll drop in, look around, and then head back to Earth stops being engineering and becomes fiction. And we haven't even talked yet about the storms themselves, the winds and megasystems on Saturn that make Earth's worst weather look weak, and that push any realistic habitation strategy from visiting to dig in and hope you last. You hear gas giant and you think cold, empty, quiet. But Saturn's atmosphere is not calm at all. It's more like permanent extreme weather. And if you try to put humans or hardware into that, you're building in a place where the storm never turns off. Start with the winds, because that alone breaks most of our Earth-based intuition. At Saturn's equator, wind speeds can hit around 400 to 500 meters per second. That's about 1,400 to 1,800 kilometers per hour, roughly 900 to 1,100 miles per hour. On Earth, a Category 5 hurricane peaks around 250 kilometers per hour, about 155 miles per hour. And we already treat that as catastrophic. Roofs ripped off, trees uprooted, cities damaged. On Saturn, that kind of speed is background noise. It's not a rare crisis, it's part of the normal circulation. So if you're thinking aerostats, balloons, floating platforms, and Saturn's upper atmosphere, understand what you're really proposing. You're putting a large, fragile structure into an environment where the baseline is faster than the most violent storms on Earth. The hull, the masts, the tethers, the balloon skins, they all live under continuous dynamic loading. You're not designing for the worst night of the year, you're designing for permanent stress every second. Over years, that means metal fatigue, seal fatigue, constant vibration, and a maintenance load that never stops. Does that sound like the kind of place you want to depend on as a pit stop before heading home? Then look at the poles, because Saturn adds something there that's not just violent, it's weird. At the North Pole, you get this stable hexagon-shaped jet stream, about 29,000 kilometers across, more than twice Earth's diameter, just sitting there, spinning. It's not a pretty pattern for posters, it's a massive, long-lived structure in the atmosphere, powered by deep energy flows that we still don't fully understand. The amount of kinetic energy locked up in those polar vortices is comparable to or greater than the energy in all of Earth's weather put together at any given time. For you, as someone designing missions and habitats, that means there are whole regions around the poles that are dynamically extreme, where trying to fly or float is asking to be thrown around by a jet stream that has been stable for decades, or maybe centuries. You don't poke that. You avoid it. Now you're carving big no-go zones into your Saturn operations map. Fewer safe corridors, tighter constraints on where you can enter, where you can glide, where you can send probes. All of that adds complexity, and complexity always pushes you to safer, more stationary designs rather than agile in-and-out trips. Now mix lightning into this atmosphere. Cassini detected Saturn electrostatic discharges, bursts of radio energy from lightning strokes that dwarf typical Earth lightning. Some of these storms produce strikes thousands of times more powerful than a normal lightning bolt on Earth. So picture that scale of discharge happening in the same environment as your aerostat, your relay satellite dipping low, or your probe passing through storm tops. For a crewed system, that forces you to harden almost everything. You need strong electromagnetic shielding around critical electronics, wiring routed and protected like it's sitting inside a giant pulse machine, surge protection on power systems, backup communication paths that survive big electromagnetic hits, Faraday cages, redundant grounding, heavy structural paths to channel currents safely. All of that adds mass and volume. More mass means more propellant if you ever want to change orbit significantly. Once again, the choice is simple. Either you design light and accept high lightning risk, which is unacceptable for life-critical systems, or you design heavy and accept that this is not a vehicle that was ever meant to sprint home. And lightning is only one part of the storm story. About once every Saturn year, so roughly once every 30 Earth years, Saturn throws a truly giant event, a great white spot storm that can wrap around the entire planet. These are planet-encircling systems, tens of thousands of kilometers across, erupting in the atmosphere with huge cloud towers and associated lightning and turbulence. If your mission timeline overlaps one of these, you don't get to ignore it. Atmospheric operations near the storm belt become extremely dangerous. Aerostats may be forced to change altitude or latitude, or they face massive shear and turbulence. Atmospheric probes could be ripped apart sooner than planned. Even orbital assets may need to shift orbits to avoid denser dust or evolving structures tied to the storm. You have to build in the possibility that for months, or even longer, certain latitudes or altitude ranges are basically off limits. That means extended no-fly periods, science lost, timelines broken. For a mission that already spans 10 to 20 years when you include the travel, one of these megastorms adds another layer of timing uncertainty you can't control. Put all of this together and ask, what kind of infrastructure do you end up with if you take Saturn's weather seriously? You're not building light, nimble craft that dip in and out of the atmosphere like tourists. You're building something more like a storm-hardened oil rig that never leaves its field, except your ocean is hydrogen and helium, your waves are supersonic winds, and your sky occasionally erupts in planet-wide storms. You overbuild everything. Thicker walls, stronger struts, more redundancy, more anchoring to a stable orbit or altitude band. You minimize movements. You design to sit in one region of space or atmosphere and ride out whatever comes. And this is the key link back to the never coming back idea. Infrastructure that is built to survive Saturn's weather is not optimized to leave Saturn. It's heavy, it has big cross-sections, it carries lots of shielding, lots of spare parts, lots of reinforcement. You don't strap giant engines on it and push it to several kilometers per second of delta V. You park it and maintain it. The crew who live there don't think in terms of next month we go back to Earth. They think in terms of next year we add another module, next decade we upgrade the reactor. So once again, the environment forces your hand. If you actually respect the winds, the hexagon, the lightning, the megastorms, you naturally design for staying, not for leaving. Saturn's weather doesn't just make your life difficult, it quietly pushes every realistic plan toward permanent anchored habitats that are totally wrong for an Earth return journey. And all of this is happening in a place that is not just violent, but also starved of sunlight, freezing cold, and brutally demanding when it comes to power. So the obvious question is, if Saturn already forces you to build huge, heavy, overprotected stations just to survive the atmosphere and storms, what happens to your chances of going home once you add in the fact that you're trying to run that entire setup in near darkness, 1.4 billion kilometers from the sun? You want to run a human outpost 1.4 billion kilometers from the sun, but out there, even the sunlight is basically saying, you're on your own. Near Earth, you get about 1 kilowatt of solar power per square meter at the top of the atmosphere, roughly enough that a few solar panels can power a small habitat if you're careful. At Saturn's distance, that drops by a factor of 90. you're down to roughly 10 to 15 watts per square meter. That's the difference between boiling a kettle and barely running a bright light bulb from the same panel area. So if you're picturing a future Saturn station with big, glossy solar wings like the ISS, scale that up, way up. To get serious power for a crewed base, you'd need solar arrays covering tens of thousands of square meters, easily many city blocks worth of area, all pointed accurately at a dim sun, all kept clear of dust and ice, all maintained by a crew that already has 100 other problems. Now think about doing that in deep space, in the dark, at minus 180 degrees Celsius. At those temperatures, gases you rely on like oxygen, nitrogen, methane, even carbon dioxide all want to liquefy or freeze if you expose them to space. Your propellants do weird things too. Hydrogen likes to escape, oxygen wants to turn every leak point into a frozen plug, valves can lock up with ice, seals get brittle and crack. Thermal control goes from being an engineering subsystem to a full-time survival job. Every occupied volume has to be wrapped in insulation, heated from inside, and kept within a tight temperature band. Lines carrying fluids need heaters, tanks need insulation, equipment bays need controlled air. Every extra watt of heating you use has to come from your main power source, which means more mass, more reactor mass, more shielding, more launch cost. Even keeping a few hundred cubic meters at room temperature and a handful of tanks at the right cryogenic points becomes a permanent, non-negotiable load on your system. Miss it, and things don't just get uncomfortable, they crack, jam, and fail. Now flip the problem. Your reactors, your electronics, your motors, they all throw off waste heat. On Earth, you can just blow air over a radiator or dump heat into water. In space, especially far from the sun, you only have one option: radiation. You have to spread that heat over a huge area and let it leak away as infrared light. That means long, thin radiators, big panels that sit in the cold of space and glow in wavelengths your eyes can't see. For a multi-megawatt reactor, the radiator area easily climbs into the thousands of square meters. That's like the surface area of several skyscrapers' roofs, bolted together and unfolded in orbit. Those radiators need plumbing, structure, deployment mechanisms, and protection. They can be punctured by micrometeoroids. They can warp from thermal cycles. They can be coated in ice or dust. Once you extend them, you don't casually retract them and stuff them back into a fairing. Structurally and operationally, they're part of a fixed facility, not something you fold up for a return flight. So when you add up the nuclear core, the shielding, the pumps, the control rooms, the radiator fields, and all the thermal control around them, what dominates your station mass? Not the crew cabin, not the little spaceship cockpit people imagine, but the power plant and its support systems. That's the anchor, literally and figuratively. You design it to survive for 20, 30, maybe 50 years. You design it to be serviceable in place. You expect to swap out parts, patch leaks, add more radiator panels, but you do not design it to be thrown away after a single round trip. At that point, calling the whole thing a ship is almost misleading. You've built a small industrial town in orbit around Saturn with heavy infrastructure, long-life reactors, huge radiators, storage tanks, machine shops, docking ports, and layered shielding. Towns don't go on road trips. You don't unbolt a power plant, fold up a bunch of city blocks, and fire them off toward another planet. You leave the town where it is. You maybe send small vehicles back and forth, but the main mass, the real investment, stays. And here's the catch that kills most "we'll come back later" talk. Any serious Saturn mission that can actually keep humans alive has to build this kind of anchored, power-heavy, over-engineered base. That base becomes the logical center of operations, the thing you keep reinforcing, resupplying, expanding. The more you invest into making it robust, the less sense it makes to spend additional insane amounts of energy and money to bring the original crew back to Earth. It's cheaper and more rational to send new people out to join them than to drag them all the way home. So by the time you solve the power problem, the heat problem, and the cold problem at Saturn, you've already made a deeper decision without saying it out loud. You've chosen to build something that doesn't leave. And when your home is a permanent town in the dark, powered by a reactor forest and surrounded by kilometers of radiators, the question you really have to ask is not when do we go back, it's what else is going to quietly trap us here next? The life support, the communications lag, or the simple fact that our whole ecosystem only makes sense if it stays right where Saturn is. You can talk about rockets and gravity all day, but here's the real choke point. What does coming back even mean if, just to stay alive at Saturn, you have to build a life support system that behaves more like a self-contained world than a spacecraft? Start with the simplest question. Where do you get your basics? Water, air, food? At Mars distances, resupply is slow and expensive, but it's still part of the plan. At Saturn, it stops being a plan and becomes a joke. A single cargo ship from Earth to Saturn takes on the order of 6 to 8 years to arrive one way. If your station runs short on water or filters or food, there is no "we'll queue up a resupply next launch window," because that next launch window still means your stuff arrives almost a decade later. That's useless for emergencies and barely helpful even for long-term planning. So for a multi-decade Saturn mission, resupply from Earth is almost meaningless. Your life support has to be closed loop. That means water recycling that hits well over 95% efficiency, probably higher. So almost every liter you drink, wash with, or flush is cleaned and reused again and again. Air recycling that pulls carbon dioxide out of the cabin, splits it, and feeds oxygen back not for months, but for decades, with no long breaks. Food production that isn't just boxes of pre-packed meals, but actual in situ generation, hydroponics racks, algae bioreactors, maybe insect farms or lab-grown protein. In other words, you're not just flying a ship, you're flying a tiny artificial biosphere that has to keep itself going while being hammered by radiation and microgravity and distance. But what happens if your loop isn't closed enough? What if you try to lean on storage instead of a true mini ecosystem? Let's look at rough numbers. A human needs around 2 to 3 liters of water per day just to drink, and that's before you even talk about hygiene, cooking, cleaning. Let's be nice and say you allow a few more liters per day for washing, maybe 5 to 7 liters per person per day total. Without serious recycling, you're looking at roughly 2 to 3 tons of water per person per year. 2,000 to 3,000 kilograms, about 4,400 to 6,600 pounds. Add food. Even compact dry rations come out to hundreds of kilograms per person per year. Assume maybe 0.7 kilograms of food per person per day. That's about 255 kilograms per year, roughly 560 pounds. And that's conservative. Over 20 years, if you didn't recycle, you'd be hauling tens of tons of consumables per crew member, easily 40 to 60 tons or more once you include some margin. Multiply that by a small crew of, say, 10 people, and now you're talking hundreds of tons of stuff that has to be launched from Earth and somehow delivered to Saturn just so they don't starve or dehydrate. That's completely out of scale with anything we can realistically push that far. So you have no choice. The loop must be tight. Water has to be cleaned and reused over and over. Air has to be kept stable without constant new tanks from Earth. And food has to be grown on site, or at least partly on site, to cut down the imported mass to something survivable. And that's just storage mass. What about the machines that keep that loop going for 20 or 30 years straight? Look at the International Space Station, right above Earth, where help is close. Life support on ISS is not fire and forget. Urine processors clog, CO2 scrubbers age, filters saturate, valves fail, pumps wear out. Astronauts spend a significant chunk of their time doing maintenance, swapping out hardware, installing new units. All of that is supported by regular cargo flights, multiple times a year, bringing up fresh parts, new filters, replacement cartridges, entire new modules when necessary. Now stretch that scenario to Saturn. You cannot schedule a new CO2 scrubber to arrive next month. A spare pump might take 7 years to get there. A critical valve that you forgot to ship with the first wave could mean shutting down part of your habitat for a decade. That's not acceptable, so you're forced into a different mode. You have to bring not just spares, but the ability to make more spares. That means 3D printers for plastics and some metals, CNC machines to shape structural parts, stocks of raw material, possibly even small foundry and electronics repair capability. Whole rooms turn into workshops. You need people trained as machinists, fabricators, repair engineers, not just scientists and pilots. All of that is more mass, more volume, more complexity, and more infrastructure that clearly belongs to a permanent base, not a temporary ship. You're basically building a small factory in orbit, because without local manufacturing, the life support system is statistically guaranteed to degrade faster than Saturn can be resupplied. Then layer biology on top of that, because your life support isn't just pumps and pipes, it's also bacteria, plants, maybe fish, fungi, algae, all interacting in a closed environment. Long isolation changes microbiomes. The mix of microbes in your water systems, your soil equivalents, your air ducts, and inside human bodies will evolve over time. Pathogens can emerge or mutate in ways that are hard to predict. Biofilms can clog filters and lines in patterns nobody saw coming on short missions. Plants grown in microgravity or in partial artificial gravity, if you spin your habitat, don't always behave exactly the way they do on Earth. Root systems spread differently. Fluids move strangely. Gas exchange shifts. Over a few months, that's an interesting experiment. Over decades, those differences can create new failure modes, from unexpected nutrient deficiencies to pest outbreaks that spread faster than your control systems can handle. And remember, the communication delay means you can't call a lab on Earth and get a rapid interactive troubleshooting session. You send data, you wait more than an hour for it to arrive, you wait more than an hour again for advice to come back. By then, a fast-moving biological problem may already have escalated. This isn't just a bigger ISS, it's a planet-scale experiment in closed ecology, and your crew is living inside it with no backup habitat nearby. So let's say you solve all of that. You spend years designing and refining systems. You build greenhouses with artificial lighting and careful nutrient loops. You lay out water recycling plants, air processors, composting and digestion units, storage tanks, bioreactors, machine shops, all tied together. After a while, it works. The station reaches a steady state. Food grows consistently, water stays clean, air feels normal. Children might even be born there and never know anything else. What does that actually look like physically? It does not look like a neat little capsule you can slide into the nose of a rocket. It looks like a cluster of big pressurized modules, wide greenhouses, thick-walled tanks, cable runs, pumps, racks, and machinery spread out along trusses. It looks like a sewage treatment plant, a farm, a small factory, and an apartment complex smashed into one continuous structure. The total mass is in the hundreds or thousands of tons. You cannot pack it up. You don't disassemble a working farm, a water plant, and a factory, squeeze them into a re-entry capsule, and shoot them back to Earth. You leave the ecosystem where it is. And once that ecosystem is there, functioning, tuned to Saturn's environment and your station's gravity and power setup, what does going home even mean? If you abandon the base, it slowly decays or dies without people. If you strip it for parts, you throw away the only working life support system in the outer solar system. The rational choice is obvious. You keep the base running, you send new crews, you let populations grow. Individuals might someday rotate out in small numbers, but the structure stays. The version of home that actually matters for survival has moved from Earth to Saturn orbit. So by the time you've done life support properly, closed loops, local manufacturing, robust biology that can run for decades, you've already crossed a psychological line. You are not camping anymore. You are colonizing. The system you need to stay alive is too big, too complex, and too tailored to Saturn to ever follow you back. And if your food, your water, your air, and your tools all now depend on that fixed ecosystem, what happens to your connection to Earth when even your conversations start to lag by more than an hour each way? And you realize you don't just live far from home, you live on a communication island that can never feel like real time again. You already know Saturn is far in kilometers, but here's the part that really messes with your life. It's also far in seconds, and that delay never goes away, no matter how good your tech is. At Saturn's distance, even light is slow on human terms. When the alignment is good, a radio signal, which travels at the speed of light, takes around 70 to 80 minutes to go one way. When the geometry is worse, it can take even longer. So every time you send something to Earth, a question, a status report, a call for help, you're waiting more than an hour just for it to arrive. Then you wait again for the answer to come back. A simple back and forth, how do we handle this error and try this fix, turns into a 2 to 3 hour round trip, minimum. That means you are permanently outside the human real-time bubble. There's no live call with mission control. No, hold on a second, we're checking. If something happens at 10, the earliest you can get informed advice from Earth might be closer to lunchtime or later. For normal operations, that's just annoying. For emergencies, it changes everything. You're no longer in a world where Earth can talk you through a crisis step by step. You're in a world where Earth can only send you guidelines and best guesses after the fact. That pushes you into a very different way of running missions. Because of the lag, you can't depend on controllers in Houston or Moscow or anywhere else to save you in real time. Software patch goes sideways and the system starts throwing alarms. You don't have time to send logs home and wait. A reactor warning light starts flashing, a coolant pump starts vibrating, 2 vehicles are on a collision course during docking. All of those things play out on timescales of seconds to minutes, not hours. You decide locally or you fail locally. So the crew has to be trained less like operators with ground support and more like a remote colony that stands on its own. You need people who can debug software, troubleshoot power systems, perform surgery, handle psychological crises, and make command decisions with no immediate backup. Your procedures, your checklists, your simulations all assume that when something breaks, the first and last line of defense is the team on site. That is a completely different mindset from something like the ISS, where controllers on the ground can watch every sensor almost in real time and help steer the response. And that independence doesn't just change operations, it changes how you feel about home. Social isolation hits harder when even conversation is broken by physics. A video call with your family at Saturn distance is almost a parody of a call. You say hi now, they hear it more than an hour later. They answer, you see their reply another hour after that. A simple chat like, "How was your day?" turns into a delayed exchange of monologues. It stops feeling like a conversation and starts feeling like sending each other long voice messages. Over months and years, that reshapes your relationship with Earth. You don't feel like someone who is temporarily away. You feel like someone who has left. Birthdays, crises, celebrations all happen with a built-in delay, and you can never jump into the moment. You never actually get to be there emotionally when something is happening. You're always late. Psychologically, you adapt. Your primary social world becomes the people physically around you, the crew, the station community. Earth slides into the background, more like a distant origin story than an active part of your daily life. And then stretch that out across the full mission timescale. You might leave Earth in, say, 2040 and not even be in a position to think about a return until the 2050s or 2060s. In those 20 years, pop culture shifts, slang changes, systems evolve, entire new technologies rise and fall. Think about the gap between the year 2000 and now. Smartphones, social media, streaming, whole new industries, whole new crises. Now apply that kind of shift again, but this time you've spent the entire period in Saturn orbit. The world you trained for is gone. The news sources you remember shut down or merged. The governments that launched you may have flipped multiple times. Entire companies that built your systems might not exist, replaced by new players who have no emotional investment in your mission and maybe no detailed knowledge of your hardware. Even language drifts. Jokes, references, memes, all the subtle glue that helps you talk to people on Earth will be different. So even if you do come back physically, there's a real chance you come back as someone out of sync with the world you're stepping into. That cultural lag matters for mission planning too. The team that champions your return phase will be dealing with people who didn't grow up with your launch, who never watched your departure, who see your mission as old compared to newer projects closer to home. Funding a giant return effort for a handful of aging Saturn veterans might not look less compelling than investing in new habitats around Mars or the Moon. The longer you're gone, the greater the probability that when a return becomes technically possible, socially it just isn't a priority. So put all of this into the head of someone designing Saturn missions. The long light speed delay forces them to treat the crew as autonomous. Operationally, they have to survive and make decisions by themselves. Psychologically, they will drift into their own culture. Logistically, the feedback loop between Earth and Saturn will get weaker as years pass. That combination makes it very hard to pretend these are commuters who will pop out for a multi-year tour and then just plug back into life at home. Instead, the crew at Saturn starts to look like a semi-independent society by default. They have their own command structure, their own way of doing things, their own timelines, their own internal stories. Earth becomes the partner and supplier, not the controller. Once you accept that, the next step is obvious. You stop lying to yourself about everyone coming back. You start writing the mission documents in a different way. These people are going to live there. They may send data, they may send children, they may someday send a few individuals back, but the core assumption is that Saturn is now their primary world. And once communications themselves push you into that colony mindset, you have to ask the next question. If the station is built like a town, the power plant is built like a town's plant, the life support behaves like a town's ecosystem, and the people operate like a town's population, what does it even mean to talk about a ship home? At that point, the real engineering question stops being how do we bring them back, and instead becomes what does a Saturn base look like if it's clearly the first piece of a new separate human civilization? If you're honest about everything we've talked about so far, you end up with a very simple engineering fork in the road. You either design something that lives at Saturn or you design something that leaves Saturn, and those two designs are almost opposites. A real base in Saturn orbit is not a sleek starship. It's a station scaled up by an order of magnitude. You're talking about thick radiation shielding around living areas, big power plants with reactors and huge radiators, long truss structures tying everything together, storage tanks, docks, greenhouses, machine shops. On top of that, you probably want artificial gravity because we already know long-term microgravity wrecks bones and muscles. So instead of one compact hull, you're assembling multiple large modules into a complex shape that's optimized to sit in one orbit and run reliably for decades. The priority is stability and maintainability, not thrust. You want something that can survive micrometeoroids, radiation, and hardware failures, not something that can survive a big engine firing. Artificial gravity is the clearest example of why this looks like a station, not a ship. If you want to give the crew something between 0.5 and 1 G without making them sick from spinning too fast, you keep the rotation rate low, around 2 revolutions per minute or less. At that rate of rotation, to get 0.5 to 1 G at the rim, your rotation radius needs to be on the order of about 225 to 450 meters. That's a ring of diameter hundreds of meters across, the size of a very tall skyscraper laid sideways in space. The structure has to be stiff enough to hold its shape, strong enough to handle internal loads, and precisely balanced so it doesn't wibble and tear itself apart. Once you've built a ring that big and that delicate, the idea of strapping huge engines to it and slamming it with multiple kilometers per second of acceleration is basically nonsense. High thrust would twist and stress the ring, stress the bearings, and pull on every connecting truss. Even if you tried to put the engines on a separate non-rotating spine and spin just the habitat, any major burn would still feed vibrations and loads into the structure. So you naturally design the whole thing to maneuver slowly, with gentle pushes, enough to tweak orbits and avoid hazards, not enough to leave Saturn and head home. The moment you commit to serious spin gravity and large radii, you've implicitly chosen station over ship. Then think about what happens over time. A Saturn base isn't static. Over the first few years, you realize you want more storage for spares and raw materials, so you bolt on extra modules. You add more backup life support hardware because you don't want a single point of failure. You add new greenhouses when you improve your farming techniques. You add more shielding when you refine your radiation models. Every upgrade adds mass. The station's total mass creeps upward every year, not downward.
Meanwhile, any dedicated return vehicle you parked nearby is aging in parallel. Its tanks are slowly outgassing, seals are drying, electronics are taking radiation hits, propellant might be degrading depending on type, and its design is locked to the tech level of the year you launched it. 10 or 15 years later, are you really going to trust that vehicle to take a crew on a 7, 8 year journey back to Earth through deep space with no easy rescue options? Ethically, that's a hard sell. You'd be putting people into a ship that is older than many commercial airplanes are allowed to be, with no maintenance base bigger than your own station. To keep your base alive and evolving, you also need proper maintenance infrastructure in orbit. That means workshops with serious machine tools, robot fleets to inspect and repair external structures, and eventually small shipyards to build and refit local vehicles. At some point, you stop shipping every specialized craft from Earth and start building or assembling them in Saturn orbit instead. You receive raw materials on slow cargo flights or harvest some from moons, then use your own facilities to turn them into tankers, tugs, and utility craft. Those local vehicles are built for in-system jobs, hopping between the base, moons like Titan or Enceladus, and maybe higher orbits for science. They're optimized for frequent starts and stops, docking, cargo handling, and short-trip reliability, not for a one-shot 15-year interplanetary cruise. They have different engine choices, different shielding priorities, and different redundancy layouts. So even when you gain the ability to build ships at Saturn, the natural thing to build is more local hardware, not a huge, overbuilt return cruiser meant to drag a handful of veterans back to Earth. And then you hit the economic logic that quietly locks everything into place. Once you've sunk hundreds or thousands of tons of hardware and supplies into the Saturn system, the ring habitats, the power plants, the radiators, the depots, the workshops, the docks, the value of that infrastructure is enormous. It's a working outer solar system hub. To send a large human-rated ship all the way back to Earth, you'd have to either strip resources from that hub, weakening it, or fund an entirely separate mega project to construct a fresh interplanetary vehicle there. Either way, you're spending a vast amount of energy and money just to move a small number of people who are already fully adapted to life at Saturn. From the point of view of any agency or company paying for this, the incentives tilt hard in another direction. Instead of paying a cosmic fortune to bring a few individuals home, you get a better return by sending more people out, more equipment, more modules. You grow the base. You increase its science output, its industrial capability, its ability to support future missions deeper into the outer system. The base becomes a permanent human outpost almost by default, because every big decision that matters favors expansion over repatriation. And this is where the idea of "you're not coming back" stops being dramatic and just becomes a straightforward consequence of design. The longer the base exists, the heavier and more complex it becomes. The more complex it becomes, it behaves like a town or a small city in orbit, complete with power grid, farms, factories, and docks. Cities don't relocate. They don't go back to their birthplace. They sit where they are and new people move in. So by the time you've engineered a realistic Saturn base, ring habitats, massive shielding, huge reactors, big radiators, workshops, local docks, you've already answered the question you started with, even if nobody wants to say it out loud. This is not a ship waiting to fly home. This is home. And once that's true, the people who go there aren't travelers on a long mission anymore. They're the founding population of a new world. You can design reactors and habitats and docking ports, but you can't design a human mind to walk into Saturn orbit, live there for decades, and then just slide back into an old life on Earth like nothing happened. That part doesn't work. On the ISS, every astronaut knows there's a capsule sitting a few meters away that in an emergency can bring them back to Earth in hours. That knowledge sits in the background all the time. It shapes how they feel about risk, how they think about their families, how they handle stress. With Saturn, that safety net is gone. Everyone on the crew knows there is no capsule you can board today or next week that will drop you into an ocean on Earth. There's no quick evacuation. No, if this goes bad, we're home in a day. That changes how you think about everything. It pushes you into a one-way mindset. In that mindset, you don't make plans around when I get back the same way you did. You stop thinking of your old house, your old city, your old routine as something you can just resume. Instead, you think about how to make life out here stable, how to keep this group functioning, how to make the station itself feel like a real place to live. Conflict and cooperation shift too. On the ISS, you know you'll rotate out in a few months. On Saturn, you're stuck with these people for years, maybe for the rest of your life. That forces a different kind of emotional discipline, or it fractures everything. You compromise more on some things. You dig in harder on others, because this isn't a temporary team, it's the core of a permanent community. Now take that a step further and ask what happens when you don't just have a crew, you start having a population. Stay long enough and children will be born in Saturn orbit, or on a moon base, or in a spinning ring. For them, Earth is a story, a set of videos and lessons, not a place they remember. Their bodies grow up under artificial gravity levels, maybe 0.7 G, maybe 0.5 G, whatever the station can provide. Their eyes get used to seeing a curved station corridor instead of a blue sky. Their idea of outside is a suit and an airlock, not a walk in a park. Bringing someone like that back to Earth into full 1G and an open environment is not a simple reunion, it's a shock. Physically, their body might struggle. Their bones and muscles might be too weak. Their cardiovascular system might be undertrained. They might need intense rehabilitation just to stand and walk without pain. Psychologically, the open sky, the crowds, the noise, the constant gravity could be overwhelming. So even if a ride home appeared, moving second-generation Saturn kids to Earth might be more like uprooting them to an alien world than going back. Even for the original crew, identity doesn't stand still. Look at how Antarctic research stations or remote oil platforms already develop their own slang, in-jokes, and social norms, and those are on the same planet with real-time contact and short flights home. Now extend that to 20 or 30 years in a closed society with a light-speed delay to Earth, in an environment nobody shares. Over time, the Saturn community will create its own language quirks, its own habits, its own rules of behavior, maybe even its own local forms of governance and law.
You'll get internal traditions, like how birthdays are celebrated, how people mark the arrival of new cargo, how command changes hands. You'll get different attitudes to risk, to family, to work. The longer that goes on, the more those people will feel like us is Saturn, not Earth. So if someday a big shiny return ship does show up, there's a real chance that you, personally, won't feel like you're going home when you board it. You might feel like you're leaving home to visit a strange planet your grandparents came from. And that shift in identity feeds directly into how you think about risk and reward. When you know deep down that you are not going back to Earth, that your life is here, your calculus changes. Earth-based mission planners sitting in air-conditioned rooms might say that experiment is too risky, or that trajectory is outside our comfort zone. But the people at Saturn might decide differently. Maybe a risky experiment could give them better crops, or more robust life support, or a breakthrough in propulsion for local travel. Maybe a dangerous EVA near the rings would unlock a huge scientific payoff. When the upside is making your permanent home safer and stronger, and the downside is added risk to people who already accepted that they are living on the edge, the balance tilts. Over time, priorities diverge. Earth might care more about clean data and long missions with low accident rates. Saturn might care more about faster progress, more autonomy, more control over their own technology. You can see the loop here. The more the crew leans into their reality, that they are settlers, not visitors, the less their mindset aligns with the idea of someday we all go back and retire in a house with a garden. That brings up the last piece, the ethics of even asking people to do this. For ISS missions, for moon missions, for early Mars missions, you can say with a straight face, the goal is for you to come back, even if the risk is non-zero. For Saturn, being honest means saying something much harsher. The only truthful pitch is along the lines of, if you go, you will almost certainly never return to Earth. You will live and probably die in the Saturn system. Anyone who signs up after hearing that isn't misled. They've already aligned themselves with a one-way journey. And that self-selection has consequences. You're not recruiting people whose main dream is to plant a flag and then come back for medals and talk shows. You're recruiting people who are psychologically ready to cut ties, to start over, to accept that their children may never see Earth. That population will see risk differently, see home differently, see we differently. By the time the first crews are picked, the idea that come back someday is part of the mission is already dead at the psychological level. The people going don't expect it, and the society they build will not be built around the assumption that everyone is leaving. So after the physics, the rockets, the storms, and the life support all push you toward a one-way Saturn, the final lock isn't the technical one at all. It's human. Once you send people who agree up front that they almost certainly aren't coming back, and they raise a generation that knows only Saturn as home, what does return even mean anymore? Especially when the rest of humanity starts to see Saturn not as the edge of a mission, but as the edge of an era. You can fight physics, you can fight radiation, you can even fight your own biology for a while. But there's one last filter that quietly decides what humanity actually does with Saturn, and that's money. This is where no one comes back stops being a dark thought experiment and turns into the boring, brutal outcome of budgets and votes. Start with scale. A serious Mars program, not a stunt mission, but a sustained presence with habitats, cargo flights, fuel depots, surface bases, and long-term science is already in the range of trillions of dollars spread over decades. That's many national space budgets over many years focused on one planet that's only tens of millions of kilometers away at opposition. Saturn is roughly 1.2 to 1.7 billion kilometers away from Earth, up to around a billion miles. Everything about it is harder. Transit times are longer, launch windows are rarer, communications are slower, power is weaker, radiation is harsher. So if Mars is trillions, a full Saturn program with multiple heavy launches, nuclear power plants, massive stations, and decades of life support research is that cost times at least an order of magnitude. You're now talking about numbers where, for the same money, you could run entire planetary-scale projects closer to home, rebuild coastal cities, transition whole nations to clean energy, terraform parts of Mars, build huge orbital infrastructure around Earth. So when someone asks a finance minister, do we pay for a Saturn return ship? The honest comparison isn't with a single rocket, it's with what else that same pile of money could do near Earth and Mars. Then look at how systems actually behave over time. Democracies think in election cycles of 4 or 5 years. Leaders want results they can point to before the next vote. Autocracies might not have elections, but they still deal with leadership changes, coups, power struggles, sanctions, recessions. Economies boom and crash. Regimes rise and fall. A Saturn mission, from initial planning to possible return, stretches 20 to 30 years, sometimes more. The government that signs off on the first wave of rockets and reactors might be gone by the time you even get there, let alone when you're ready to come back. 3 or 4 administrations down the line, the people in charge will be balancing different priorities, responding to different crises, listening to voters who were children when you launched. The probability that the exact same system that paid for your departure is still intact, motivated, and rich enough to fund the massive return effort decades later is low. It's not zero, but it's low enough to bet your life on it is a huge risk.
Now factor in how stories are told. Once you've successfully built a Saturn outpost and kept it alive for a few years, the narrative that sells best back on Earth is not "we brought them back," it's "we expanded humanity's footprint." Headlines like "Saturn Base 1, humanity's farthest home" sound powerful. They tell a story of courage, progress, and frontier building. That is easier to sell than "we spent another $1 trillion so 3 exhausted people could retire in a house in Houston." Once you've spent a gigantic amount of money and mass to establish a permanent station, justify it, and celebrate it, it's easier to ask for more money to grow that success, to add new modules and send new crews. It's much harder to ask for even more money to end it or to peel people away from it. Funding tends to flow toward expansion because expansion looks like forward motion. Repatriation looks like walking backward, like saying, "we did all that and now we're undoing it." Meanwhile, Earth does not pause while you orbit Saturn. Back home, you still have climate change pushing sea levels and weather extremes. You still have wars, pandemics, financial crashes. You have entire regions asking for disaster relief, rebuilding, support. When a committee sits down and looks at where to allocate limited funds, they see line items like upgrade flood defenses for tens of millions of people, stabilize food supplies in regions hit by drought, invest in energy transitions, and then in another column, multi-decade Saturn return program for a small crew in their 60s. Even if everyone respects the astronauts, that line can look like an indulgence when stacked against urgent human needs on Earth. The return leg is not required to keep the Saturn base alive. It's not required for ongoing science. It's not required for national security. It serves a moral purpose, bringing pioneers home, but it can look like a luxury. When budgets tighten, discretionary lines get cut first. A Saturn return ship, with its huge cost and limited constituency, lands right in that danger zone. Once you skip funding the return once or twice, you establish a pattern. Budgets get written with assumptions. Planners start treating supply missions, science payloads, and maybe occasional new crew rotations as the core program. The idea of a dedicated, heavily funded return architecture fades from the planning charts. Instead, you get incremental expansions, another power module, a new lab, a bigger greenhouse. Insurance for the people already there becomes focused on keeping the base stable and well supplied, not on bringing them back to Earth. That's what policy lock-in looks like. You define Saturn in practice as a one-way frontier, even if you never put that phrase in a press release. The first few mission design cycles that skip a return system set the precedent. The next generation of planners treat Saturn base as a permanent asset, not a temporary deployment. Young engineers grow up assuming Saturn is where you go to stay. Language shifts from mission to colony, from crew to residence. By the time anyone seriously revisits the idea of large-scale return, the entire ecosystem, budgets, public expectations, international agreements, industrial contracts, is tuned to support staying, not leaving. The people on Saturn may even push back on spending enormous resources just to move them personally. They might prefer those resources be used to make their homes safer, larger, more independent.
So after gravity, distance, radiation, engineering, biology, and psychology have already pushed you toward a one-way Saturn, economics deliver the final shove. Not because someone decides to trap you, but because every rational funding decision, made year after year, tilts in the same direction. Saturn becomes cheaper, safer, and more useful if people stay, and brutally expensive if everyone insists on coming back. And once Saturn is locked in as a one-way frontier in our budgets and laws, the last question left isn't how do we bring them home? It's something bigger. It's whether crossing that line, turning Saturn into a place we go to and don't return from, is just one more mission, or whether it's actually the edge of an era in human spaceflight that we never cross twice. Here's a blunt truth that sits underneath everything else. Saturn is pretty much the outer edge of what chemical rockets and human bodies can handle in the same mission. And once you step over that edge, you're not treating spaceflight the same way ever again. In raw energy terms, Saturn is already pushing it. With today's engines, chemical rockets pushing exhaust out at a few kilometers per second, you can just barely stack enough delta V to get humans from Earth out to Saturn, slow down, live there, and theoretically get back.
but only on paper and only with extreme, probably unrealistic engineering. Go farther to Uranus, Neptune, or the Kuiper Belt, and the numbers start to demand propulsion we simply don't have yet. High-thrust nuclear, fusion, or something even more advanced. So Saturn ends up as a kind of practical threshold. It's the last big world you can reach with classic rocketry and not instantly kill everyone. That makes it the edge of a whole era of human spaceflight, the era where we push chemical technology and traditional mission architectures as far as they will go. You cross that line with people, and you're basically saying, this is as far as we can get with this kind of tech, and we're not planning on doing multiple round trips. So how does that feel in human terms? On Earth, we've seen this pattern before. People have always done journeys where they knew they weren't coming back. Polynesian sailors pushing out into the Pacific, loading canoes with food and water, not knowing if there was any island ahead. Early Arctic and Antarctic expeditions heading into ice with no guarantee of rescue. Migrations across land bridges tens of thousands of years ago when groups left one continent and slowly, over generations, filled another. Those moves weren't tourism. They were one-way bets. Saturn is that same logic, scaled up to the level of an entire technological civilization. Instead of a canoe, you have a multi-stage rocket. Instead of an island chain, you have moons and stations and rings. Instead of a few hundred kilometers, you have more than 1 billion. But the core decision is the same. Some people go, and they understand that home is not a place they're going back to. It's a place their descendants might only know from stories and data. Zoom the camera way out in time for a moment. On cosmic scales, even a Saturn colony is tiny and temporary. The rings themselves may mostly disperse in a few 100 million to 1 billion years, slowly ground down by collisions and pulled into the planet. The sun will gradually get brighter and hotter over billions of years, changing the climate of every world in the system. Saturn's atmosphere will keep evolving. Against that backdrop, a human presence that lasts, say, 10,000 years is just a tiny blip. But on human timescales, that same presence is effectively permanent. A base that survives and grows for a few centuries would outlive multiple nations, empires, and economic cycles on Earth. A community that stays in Saturn orbit for 1,000 years would outlive entire ages of our history. By the time cosmic change actually threatens their existence, they might have moved farther out or transformed completely. So yes, in the deep future, nothing is forever. But for you, for anyone alive in the next few hundred years, a Saturn colony is about as permanent as things get. Now pull the camera back in and think about what life there actually becomes. Whether you're in orbit, on Titan, or in free-flying habitats in the Saturn system, your day-to-day reality is different in every direction. Lower gravity than Earth, much weaker sunlight, a black sky with a huge striped planet hanging in it, rings cutting across the view, different lengths of day and night, different seasonal cycles. The rhythm of life is set by station rotations, moon orbits, power management cycles, and communication windows. At some point, that adds up to a new world in every practical sense. Not just a base with people, but a world with its own gravity level, its own sky, its own rules. Coming back to Earth from there wouldn't feel like flying home from another country. It would feel like moving to a totally different biological operating system. Different standard G, different atmosphere, different light levels, different risks. Your body, your habits, your mind, all tuned to Saturn's environment, would have to adapt again. And that adaptation might be harder and less appealing than just staying where you already fit. So put every layer together: the energy limits of chemical rockets, the distance and time, the bone loss, the radiation, the ring debris, the deep gravity well, the closed-loop life support that behaves like a tiny planet, the 1-hour communication lag, the spin gravity megastructures, the autonomous station culture, and the harsh reality of multi-decade funding, and ask the final question: with the technology we can realistically build this century, what does going to Saturn actually mean? It doesn't mean we do an expedition and then everyone comes back for parades. It doesn't mean we send people like ISS crews on rotations. It means something much more one-directional. The physics of distance and gravity makes a full round trip insanely expensive in fuel. The biology of long-term space living makes a return to 1G questionable for your body. The engineering of big, stable habitats and power networks makes your infrastructure too heavy and complex to ever move. The economics push money toward keeping the base alive and growing, not on dragging the original crew back. So if you go to Saturn with any plausible near-future technology, you're not really going on a round trip. You're stepping through a one-way door. On this side, Earth is a default home. Chemical rockets are the main engine, and missions are designed with return baked in. On the other side, Saturn is the primary world. Advanced stations are permanent, and people are expected to live and die there. You don't come back to Earth as someone who finished a mission. You stay and you become part of the first human civilization that lives under a dim sun, in the shadow of a ring giant, and eventually you stop thinking about going back at all. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.